Greetings and welcome back. Today we're going to be looking at how we create the simplest of amines, which are primary amines. So these will be the reactions that result in formation of something that looks like this. Essentially ammonia attached to only one R group. When you look at that reaction, it might seem like there's a very straightforward way to do this, and there is a very straightforward way to do this. If you recall the fact that ammonia acts like a nucleophile, then we would just need to have an R group with a leaving group, which would just be an Rx. The mechanism for this reaction would just be the nitrogen attacking the R, kicking off the leaving group, and after a little bit of base or something like that, you would indeed get a primary amine. There is a slight problem with this reaction, however, one that took a long time for organic chemists to get around. So the problem with this reaction is that at that point, after you've done this once, you would probably still also have some ammonia hanging around. And you would probably also have some Rx hanging around. And unfortunately, this guy, the quote-unquote product, is a better nucleophile than your starting material was. And that can give you secondary amine. And of course that guy can react again and give you some tertiary amine. And of course that guy can again react and give you some quaternary amine. And of course you'll still have some of your primary amine hanging around. And you'll probably also have some ammonia. So, the reason that this reaction is really no good is because you end up with a complicated mixture of ammonia, leftover unreacted ammonia, and primary amine, and secondary amine, and tertiary amine, and quaternary amine. And there's not really too much that you can do to prevent that. So what looks like the best and most straightforward answer to this question of how do we create a primary amine actually turns out to not be that great of a reaction at all. There's one way that you can kind of get around this, and that is just to fool around with stoichiometry. So in this exact reaction, we tend to use iodine because iodine is the least basic of all, but any alkyl halide would work. If you use a vast excess of ammonia and react it with your alkyl halide, you tend to get primary amine, and then you end up with lots of leftover amine or ammonia. In this case, just because, let's say that we have 1,000,000 of these for every 100 of these. All right, that's a vast excess, probably way too much. But after the first one reacts, we would end up with 999,999 of these left over, and we would have one of those left over, and of course we would have made one of these. What is more likely to react with the second portion of your alkyl halide? Is it the 999,999 of these, or the one of those? While this would be a better nucleophile, this is what you would get a lot more reacting, just based on probability. So if you have an entirely enormous amount of ammonia left over, then just on probability, you'll end up making almost all primary amine with a lot of leftover ammonia. What you would want to do after that, and this is really easy to purify, you just heat it up. Ammonia is actually a gas at standard temperature and pressure. So you just boil it out and you'd end up with your primary amine left over. So this is an okay way to go about it. There's still a chance that you could get some secondary or tertiary or quaternary amines. And also we don't usually like to work with vast amounts of excessive ammonia just to boil it off at the end. So chemists have come up with a number of other solutions of how to make a primary amine, and just take my word for it, what's on this page is not really optimal. Probably the best known alternative way of creating a primary amine is called the Gabriel synthesis, named after a chemist named Gabriel, not the angel. But the Gabriel synthesis is one way to make sure that you only end up with one amine attached to your alkyl halide. And the way that he did this was to start with a complicated looking molecule called phthalimide. Phthalimide is a diamide. You can see that it's got an amide over here, C double bond O NH, and also an amide over here, C double bond OH, with an aromatic ring attached. So the way that is spelled is PHDHALIMIDE. So that's another good word for you to use in Scrabble, phthalimide. The reactivity of this molecule is that NH at the far right side is actually incredibly acidic. We can react this with some KOH, and you'd pull that hydrogen off, giving you an N-. Normally, we can't generate an N- very easily, but in this case, the reason that it's so acidic is because of the resonance of the conjugate base. There would be resonance structures where you could move this negative charge around to that oxygen or that oxygen, and therefore having a negative charge spread over two oxygens is actually quite stable. So this guy is quite stable, but it actually still retains the reactivity of an N-. You can at this point add in, and this would be your second step, whatever alkyl halide you want. And the nitrogen, the N-, would attack that R group and kick off your leaving group, kick off the halogen. At this point we would have our phthalimide. Instead of having an NH at the end, it would now have the N attached to an R group. You'll notice that at this point there is not going to be any possibility of a second reaction. The lone pair on that nitrogen, the second lone pair, is going to be involved with resonance between those two carbonyls. Therefore, this nitrogen cannot possibly act like a second nucleophile. Therefore, it cannot possibly put a second R group on. So you can add a stoichiometrically equivalent, or that is to say 50-50 mixture, molar-wise, of your alkyl halide and your deprotonated phthalimide, and you will only ever get a nitrogen attached to one R group. What we can then do is to remove that nitrogen using a little bit of hydrazine, H2N and H2. And the hydrazine will actually embed itself, and this is not that complicated of a mechanism, but hopefully you'll get the idea here. It will kick off, both of those nitrogens will get embedded into kind of between the two carbonyls of the phthalimide, and will kick off this part. So this is just a side product here. It would be a phthalimide hydrazine, but that's not really what we're after. What we're after is that you would kick off that N with two H's that would come from the hydrazine, and we would make NH2R. And this is that primary amine, which has no chance of having a second R group attached. Therefore, it's, I wouldn't say 100% yield, because nothing's 100% yield, but an extremely good way to make a primary amine without wasting a whole lot of ammonia or without having any possibility of secondary or tertiary amines. There are a few other ways to do this with an alkyl halide, which have been developed more recently. The first is using sodium azide, or NaN3. I'll draw out the N3. It would be N double bond N double bond N. So the nitrogen in the middle would be a plus charge. Two nitrogens on the end would both be minus charges. And of course the sodium is also a plus charge. So that's how that molecule works out. It's actually stable enough. You can buy this in a pot. And you can react it with an alkyl halide. Of course, both of those nitrogens at the end can be nucleophilic, but only one of them will act as a nucleophile at a time. This would give you a product where you would have this big old nasty N3 thing attached to your R group. And now you would only have one N plus and one N minus, and therefore those two things kind of cancel each other out, and it's not going to be reactive anymore. At this point, obviously this is not a primary amine, but what we can do is reduce that guy down. And you can use either lithium aluminum hydride, which is a great reducing agent, or you can add hydrogen and palladium. So these are both of the ways that we had to reduce carbonyls, and it turns out they work for reducing this azide as well. And it will take off the two nitrogens, and you will end up making NH2 attached to an R. So it basically just cuts it off there and reduces that nitrogen down to an NH2. So there, you've got a primary amine. All right, the second way to do this would be to start with cyanide and triple bond C minus. Sodium cyanide or whatever. This guy would act like a nucleophile as well. You would attack an alkyl halide, kick off the halogen leaving group, and we would generate an N triple bond C to an R group. All right, again, this is not a primary amine, but we could reduce it down. You'll notice that once again, if you turn that nitrogen into an NH2, you can also reduce this carbon to a CH2. You wouldn't have to break any single bonds. And so we can do this reaction with the exact same things. We can either use LAH, or we can use the same thing as above, hydrogen and palladium. Of course, platinum would work as well. And in this case, we will reduce down both of those, the nitrogen and the carbon, and it would turn into an amine attached to a CH2 in an R group, which is again a primary amine. There's a slight difference here. You'll notice that in one case, you started with this R group and you've just stuck on the amine. In this case, you've started with the R group and you've not only put on the amine, you've put on a CH2 amine. So this lets you make your carbon chain one carbon longer and attach the amine as well. In the first case up here with the sodium azide, you start with the alkyl halide and you only are adding on the nitrogen. So essentially the sodium azide method would be pretty much the same as Gabriel synthesis. You would get the exact same thing. You might want to use one versus the other for some reason. But the one below, the one where you use cyanide, this does something actually a little bit different. It puts on a CH2 and an NH2 at the same time. So it makes a slightly different primary amine. There's one more method I'd like to introduce to you today that lets you make primary amines, and that is the reduction of a nitro group. A nitro group is less commonly found, really, than anything else, except for one location, and that is on an aromatic ring. You may remember that it was really easy to put a nitro group on an aromatic ring, and so this is a way that we can turn that nitro group into amine if that is necessary. So this is usually about making aromatic amines. The way that we do that is we can start with that nitro group and reduce it using the hydrogen and platinum, or palladium yet again. But in this case, this guy's so easy to reduce that we will often use nickel because nickel is much cheaper. So palladium or nickel. Right? Nickel is much, much cheaper than palladium or platinum. The other way that we can do this, you might remember the Clemmensen reduction. The Clemmensen reduction was a reaction in which we started with a carbonyl and converted it down to a CH2 using zinc and mercury and some acid. But we can apply the exact same thing here. We can use H+, so this is an ore. Yet again, you have multiple ways of reducing things. You can use the hydrogen, or kind of the acid and zinc. Once again, we have our choices of metals. You could also use tin or iron. And all of those would reduce that nitro group down to an NH2. So that would be another way to make a primary amine. But in this case, we're not starting with an alkyl halide. We are starting with an alkyl nitro group, or a nitroalkane. Alright, so that is the last reaction I'm going to show you today. In the next lecture, we'll talk about how to make secondary and tertiary amines. As a bonus, there'll be one more way to make primary amines, in addition to a way to make quaternary amines. So, but study these reactions, and I will see you in class.